Let's see. In carboxylic acid, first thing we need to understand that these were the most earliest organic compounds which were discovered. So before even framing the IUPAC rules, there were a lot of acids which were already existing. Okay, and they were in use. So more than IUPAC naming, their common names becomes more relevant. So we will have to use their common names more often. For instance, if you notice HCOH, formic acid, then acetic acid, butyric acid, valeric acid, okay, oxalic acid, very common ones. Okay, those are both accepted as IUPAC as well as their common names. Then we have dioic acids. When it comes to dioic acids, you notice that if you do not have any methyl in between, that is oxalic. If you have one methyl, malonic, two methyls, succinic, three methyls, glutaric, four methyls, adipic, five methyls, pimelic. These are few important names we should know. Along with that, some acids which are used, during the chemical reactions or as a part of some application, you will be using this one malic acid, which is a cis form of this dioic acid. The trans form of the same is called fumaric acid. Benzene with a COH is benzoic acid. If you have two COH, it is called phthalic acid. And at ortho, it is called phthalic. At meta position, it is isophthalic. Para position, it is called terphthalic. And if you have COH and NH2, it is called anthranalic. And lastly, if you notice, lactic acid, tartaric acid, and citric acid. These are also quite useful ones. This is barbituric acid, which does not have a COH group. So basically, it's an amide group. Got it? Without any COH group, but have sufficiently acidic nature. Clear?
Yes, ma'am.
How do we prepare the acids in general? We can again list out from all the various functional groups, starting with alkenes. Alkenes, when you react in the presence of air with catalysts like manganic acetate, it will convert that alkane into acid. Methane plus O2 will give you formic acid. This is one of the most relevant reactions you will find. Next comes alkenes. Alkenes on oxidation, you would notice the bond breaking between carbon and carbon occurs. It is usually done with concentrated KMnO4 or concentrated K2Cr2O7. On breaking the double bond, you can get acids on either sides. Same can be done with ozonolysis also, but it has to be oxidative ozonolysis. It means we need to use some peroxide along with ozone so that that double bond breaks and converts into an acid form. Next one is a Koch reaction, wherein a double bond reacts with CO and HCl, where HCl will combine with a Lewis acid AlCl3 to release H+. Pi bond will accept that H+, creates a carbocation, and the carbocation further attacks on CO and thus getting a positive charge on carbon. Thereafter, on hydrolysis, it will convert into an acid. So this is another typical way of getting acids from alkenes.
Okay.
Next, alkynes, again we can process through ozonolysis or KMnO4. Alkyl halides, you can convert alkyl halide into Grignard's reagent first, react that with carbon dioxide. Here R possesses minus charge, carbon possesses positive charge. So that would attack on carbon, trying to produce this carboxylic acid form. Alkyl halide, when you react with Cn minus will attack, X minus will leave, converting into alkyl cyanide. This on hydrolysis will give you amides, which on further hydrolysis will give you acids. Either in acidic medium or in basic medium, you will get to see that as acid form. Okay. Partial hydrolysis will create amides. but complete hydrolysis will create acids. The mechanism for this particular area is important in this topic. Let me show you. If you do it in acidic medium, the lone pair from nitrogen will first extract proton that activates the carbon to have sufficient positive charge so that it can attract a nucleophile. Nucleophile in this case is water because you're doing hydrolysis. And then nitrogen's lone pair regains, and the lone pair will take away H plus internally, making it as NH2 plus. Furthermore, oxygen will push the electron, pi bond will go. Again, internally, one more time, H plus will be pushed in. So that way, NH3 plus will be formed. And NH3 being a good leaving group, water will attack, ammonia will come out. And on that, ammonia again acts like a base, takes H plus from this conjugate acid, converts that into RCOOH. So these are the products that you will see in acidic hydrolysis.
Okay.
What will be the products in basic hydrolysis? OH minus will attack carbon, pi bond will shift onto nitrogen. Nitrogen will take H plus from water, that will convert into an enolic form. Enol undergoes tautomerism because you can see there is ene and ol. So that will make it amide after tautomerism. Then OH minus as a nucleophile will attack. But now is the challenge. Even though oxygen pushes down, both OH and ammonia are good leaving group.
Mm.
But if you put more concentrated OH minus, then removing OH minus will be difficult because the reaction will be trying to push in the forward direction due to concentration of OH minus. So alternatively, you will expect NH2 minus to leave, but it's a very poor leaving group. That's why we require heat. Okay. So heat is to be facilitated to remove NH2 minus, and thus you can get this as acid. And NH2 minus can take H plus from this acid, converting into RCO minus. So these two are typical mechanisms of acidic and basic medium. Just go through it for a minute, then we'll go ahead.
So done.
Yeah, next. Notice how we get it from arenes. In case if you want to make acid on benzene, we need to have a methyl group on it. This we have done it in benzene chapter, wherein the side chain gets oxidized in the presence of an oxidizing agent like KMNO4, HNO3, or K2Cr2O7. It would oxidize this carbon into COOH. In fact, if the carbon is sp3, its requirement is it should have at least one alpha hydrogen. Okay. If it does not have an alpha hydrogen, then oxidation does not take place. What I'm trying to say, suppose if you have carbon with three other carbon connections, like let's say tert butyl group here like this. And then if you're trying to oxidize it, nothing will be observed. Why? If at all you have at least one hydrogen here, you can see there is at least one hydrogen here at alpha position. Then KMNO4 or K2Cr2O7 can easily initiate the reaction, make a nascent oxygen to insert between carbon and hydrogen, thus making it as oxidation reaction. Therefore, you will get this as benzoic acid. Clear? Even if you have a ethyl group here, so between these two carbons, if you see again, the bond breaking can happen and this carbon will convert into benzoic acid here. Okay. And this carbon hydrogen bond, if at all, again, I'll break between these two. These two carbons will also break down, convert into carbon dioxide, leaving behind benzoic acid. If at all I have a double bond or a triple bond, then there is no compulsion that we need to have alpha hydrogen. Even if it does not have, bond breaking will take place and you'll get benzoic acid. Okay, beta?
Okay.
Now, by chance, if you have an oxygen connection already existing, it will only catalyze the reaction to go even faster, making benzoic acid faster. Okay.
Okay.
So you can see all of these cases, these two will convert into acid. So phthalic acid. Here also these two bonds will break. First you will get an oxalic acid. Along with phthalic acid, you'll get oxalic acid. But oxalic acid with MnO4 minus in acidic medium will get further oxidized. Okay. So in short, these two carbons will also eventually convert into carbon dioxide. Here you can see again, as you break, this will be oxalic acid, this is carbon dioxide, and these two carbons will be uh, phthalic acid. Out of all of these cases, these two cases are important to understand. That is, if two different activated rings are present, now you notice that this ring versus this ring, if you compare, the second ring is more activated because OH is a donating group. And typically, when oxidation happens, it will always happen on a more activated ring first. So that means this bond will break, leading to phthalic acid. But if you compare the next case, wherein this ring is more activated than the nitrobenzene ring, so nothing will happen here, correct? Oxidation will take place here. So you have to break it here. So as you break that, you will get this nitro will be preserved on this benzene ring. This benzene will break and convert into COOH. Okay.
Okay. Yeah.
And if you have a cyclic ketones, there also you will see bond breaking will take place because cycloketones on heating can be expected to show more enol character, and enol have a double bond which can break and convert the carbons into acids on both sides. That's how we can get adipic acid as well. Okay.
Yeah.
Next, how do we get acids from alcohols? See, if at all I have 1 degree alcohol, on oxidation, you will get carboxylic acid. This we have learned in alcohols already. Let me revise.
Right.
KMNO4, K2Cr2O7, CrO3 acetone, which you call it as Jones reagent, and even concentrated HNO3. All of these would help alcohols to convert into acids, primary alcohols. If it is secondary alcohol, you will not be able to convert that into acid. It will end up at ketones. But if the secondary alcohol is connected with a methyl group and then you treat with iodine or halogen NaOH, it will go for haloform reaction. And haloform reaction is removing out this carbon, converting that into an haloform. And the rest of the part will convert into an acid. Okay.
Okay.
Same logic in the next case also, same logic in the next case also. Got it?
Yeah.
Here, all of these are haloform reactions. How do we get acids from aldehydes and ketones? From aldehydes, we know these are the three famous oxidizing agents, toluenes, phthalates, and benedicts.
Mm.
Alongside, we can also add KMNO4, K2Cr2O7. Okay.
Okay.
KMNO4, K2Cr2O7 does not have a controlled oxidation part. That means if you have a double bond, it will break there also. but these three will have only controlled part. That means they will only and only oxidize aldehyde part. So for example, if you want to convert this into this, then the better oxidizing agents used are toluenes, phthalines, and benedict. Okay. Next comes, if at all I have acid chlorides. Okay. See, earned Eisted reaction. If we talk about earned Eisted reaction, how does it take place? See, if at all I have an acid chloride reacting with diazomethane, CH2 minus and N2 plus, then this CH2 minus will attack, Cl minus will leave and leading to this part. Okay.
Okay.
Now, this CH2 minus is surrounded by two strongly withdrawing groups. N2 plus is a strongly withdrawing group. C double bond O is also strongly withdrawing. That makes this carbon to have acidic strength, which means the second mole of CH2 minus, that diazomethane, will again take H plus from here, gets a negative charge on carbon. Got it? Negative charge on carbon. And once you get that, it will push, Wolff rearrangement is possible, wherein we learned how the Wolff rearrangement works earlier. Actually, in fact, from here onwards, you learn it more often. Okay, so let me explain you what happens. See, Wolff rearrangement is a case where you will have a C double bond O with some alkyl group, then connected with a group which has a good leaving group again.
Okay.
So in that case, what happens? This leaving group will try to initiate the bond breaking. As it happens, this particular carbon, nitrogen, whichever group present here, it will have a loss of octet. To compensate that, the alkyl from here will shift onto it. While shifting, it will come out as a alkyl anion.
Mm.
So which means it leaves a positive charge on nitrogen. And that positive charge is compensated by this negative charge, making a double bond. Okay, this thing happens simultaneously, and this rearrangement is called Wolff rearrangement. Okay, due
Okay.
to this, you would be getting a compound called ketene. Okay,
Yeah.
and ketene on hydrolysis. Okay, so that means you just have to break the bond here. If you have H2O, okay, OH can be added here. Sorry, where is that? Here, yeah. This will take away minus charge here. So minus will take away H plus from here. OH will come here. So what is left out? Acid. Done. Ketones are extremely useful because it can be used to convert into any functional group. Okay. For
Okay.
instance, you see with water it can convert into acid. With ammonia it will convert into amide. With
Mm.
alcohol to esters. With HCl to acid chlorides. With acid again it will become an anhydride. Step is simple. Here this
Mm.
carbon has negative charge. That will take the H plus which is incoming. This carbon will take the nucleophile. Okay.
Okay. Yeah.
Right. Notice this one. Check. If it comes to acid derivatives, compounds which on hydrolysis will give respective acids. That is, if you have an acid chloride, all of this, that on hydrolysis will give you acids.
Mm.
That is why they are called acid derivatives. Okay. Even if you have an acid chloride here in acidic medium or a basic medium, H3O plus also you will get this. OH minus you will get this. Okay.
Okay.
Right. Next from carbon monoxide. RO minus, when you react with carbon monoxide, it will convert into RCO minus. Okay. Typically, how does it work here? You have C triple bond O minus and plus here. Okay. Clear? And now, when you are pushing this RO minus, correct? So basically, you are making this as RO minus, sorry, R minus to connect with carbon because this bond will shift onto oxygen, making it as a double bond here, correct? And
Yes.
as it goes away, it will become neutral. And that's when the connection has come here, right? Like this, isn't it?
Hmm.
Here.
Yeah.
So as it grows here, from this position, it will push into a double bond here, correct? R minus will shift here and O minus will go. Can you see it is just like Wolf rearrangement again?
Yeah.
So that will lead into formation of RCO minus, okay?
Okay.
And that on hydrolysis will give you acids, okay? So RO minus with carbon monoxide. But this requires a strong heating, okay? You will read this again in group 14, okay? That is how carbon monoxide reacts to get acids, okay?
Okay.
What are the general properties of acids? You see, C1 to C9 are colorless liquids. They are pungent smelling. C9 and above, they are waxy solids and odorless. Carboxylic acid generally has higher melting point and boiling point due to the strong hydrogen bonding they possess. Okay, intermolecular hydrogen bonding is observed. Now, intermolecular as in if you have R, C, double bond O and H, this side also it will extend its hydrogen bonding. This side it will extend its hydrogen bonding. This side and this side. So you can see per molecule it will have 5 hydrogen bonds.
Yeah.
So that way when it connects with all other molecules, it will have a strong hydrogen bond character because of its boiling point and melting point would be higher. When you add it in vapor state, when you add it to an aprotic solvent or a non-polar solvent,
Hmm.
instead of showing more intermolecular as a chain form or showing an intermolecular with a solvent, now they will show intermolecular between the molecules, by which they will end up forming like a cyclic structure as a dimer. That's why if you notice benzoic acid also, if at all I take 2 moles of benzoic acid C6H5 COOH, okay, and keep it in benzene. As soon as you keep it in benzene, this will convert into C6H5COOH twice. Twice means it has become dimer. Got it?
Okay. Yeah.
C4, up to C4, simple acids are soluble in water due to strong hydrogen bonding. But as it comes to benzoic acid or larger carboxylic acids, larger alkyl group carboxylic acids, they would remain insoluble, especially in cold water.
Hmm.
Okay. All dicarboxylic acids are solids, right from forming oxalic acid, correct?
Yeah.
Oxalic acid onto any other acids, they usually exist in solid form.
Hmm.
Okay. Now, the typical pK value of acids is 3.5 to 5.5. Okay. And if you notice the pK value of other compounds here, so pK value of, hydrogen or methane, correct? Or pK value of carbon dioxide, which is carbonic acid, right? Or water, okay? Or pK value of phenol, PHOH, or acetic acid, CH3COOH. If you compare all of them, remember this is 38 and 38, okay?
Hmm.
This is 6 and 15.7. Phenol is 10, this is 25, okay?
Okay.
This clearly shows that acid is a dominant, carboxylic acid is a dominant strength compared to that of these acids,
Hmm.
okay? Which means wherever there is a chance of releasing these compounds, acid will help in releasing it. And that's why you'll see sodium, if it provides electrons to hydrogen, it can come out as H2 gas, right? Because the pK value. Second, if you have NaOH, acid-base reaction can take place. It will give H2O. Why? Because pK value is quite higher here. That means it's a very, very weak acid.
Okay. Yeah.
Bicarbonate will give you carbon dioxide, correct? So that's why it is said that it will give positive bicarbonate test. This is
Okay.
carbonate test, it will give positive carbonate test. It will give positive phenoxide test. That means even when you react with phenol also, that is PHO minus also, you'll expect this to become RCO minus and PHOH. Got it? Acetate also same thing. So that is, if you have HC triple bond C minus, you will get this as RCO minus plus HC triple bond CH. Got it?
Okay. Yeah.
This is the acidic reactions which we can expect from carboxylic acid. Okay.
Mm.
Next, how does carboxylic acid respond to ammonia? If you have a COOH react with ammonia, it will give you ammonium salt, and that on heating, correct, you will be able to remove out water first, H2 from here, and oxygen can be removed out to convert this into amide. Okay.
Mm.
So this is a two-step reaction. Students usually get confused here. It's a two-step reaction. First is an acid-base reaction.
Yeah.
Only when you heat it, that's when you get amides. Okay. So
Mm.
without, if the heat is not given, then you'll stop here only. Okay. Now that can be shown with phthalic acid also. Phthalic acid, when you react with 2 moles of ammonia, first you will get ammonium phthalate as the salt. And only when you heat it, water will be lost and you'll get amides on both the ends. But on further heating, if you further heat this, even ammonia will come out of it now. This one, ammonia will come out of it, and one of the nitrogens will connect onto the second C double bond O group, makes it into a new compound now known as phthalimide. The preparation is very important. Going ahead, we'll be using this reaction multiple number of times. So remember how it is being done. Phthalic acid converting into phthalimide. Okay,
Okay. Yeah.
right. Carboxylic acid specifically is used for dehydration. Okay, that means if you have a carboxylic acid, you can dehydrate or remove water out of it and convert into some new compound. We require some strong dehydrating agents like P4O10. So if I use P4O10, I take 2 moles of acid here, that will convert into an anhydride.
Mm.
Okay. And similarly, if I use P4O10 and heat, here also I can convert this into an anhydride form. Okay. Same way, if you have HCOOH, I can get carbon monoxide and H2O. That is also
Yeah.
dehydration. If you have COOH and concentrated H2SO4, देखो, remove one carbon dioxide, one water. What is left? Carbon monoxide. So these three will come.
Okay.
With aluminum phosphate, instead of removing, acids like this and making an anhydride, aluminum phosphate helps in making a dehydration internally. So the OH from here and H from here can be removed internally, and that brings you ketenes.
Okay.
Done. Next, carboxylic acid's main reaction. So far, whatever we have discussed, right? Most of them were repeated ones, except that Ernst-Eistert reaction, where Wolff rearrangement happened. Rest all were something which we learned beforehand, right? Now,
Yeah.
this part is the important part from carboxylic acid about what happens on heating effects. Okay. Now, in heating effects, we will take two compounds. One is hydroxy acids, the other one is amino acids. Hydroxy means where you have an OH group. Okay.
Yeah.
OH group could be present on an alpha position, beta, gamma, delta, epsilon, or any higher positions. Okay. So we will try to figure out what is the product on product we will get when OH is present on different positions, starting from alpha. If at alpha position we have OH group, then as soon as you heat it, you will see the dehydration starts, but between two molecules. Got it? What
Okay.
is this dehydration exactly? Basically, it is an esterification.
Mm.
You can see the alcohol from one molecule is combining with acid of another molecule. So it is an esterification. So likewise, it happens on two sides, converting that into a cyclic structure. So it will be a cyclic diester.
Okay.
Tana clear beta?
Yes, sir.
Right, next. If you have beta hydroxy acids, okay, so here you can see beta hydroxy acid is present.
Hmm.
If at all we heat that, this OH and H can be removed out and you will get a double bond here. That's how we can get alpha beta unsaturated acids.
Okay. Yeah.
Clear?
Yeah.
Next is gamma hydroxy acids. So you can see this OH and COOH. This could be removed out, converting into a cyclic structure. So which is gamma lactone.
Hmm.
Okay. Next we have delta hydroxy acids. If it is delta hydroxy acids, okay, this OH and C double bond O, you can remove out the water out of it and you will get delta lactones. Okay.
Yeah.
What have you learned from here? See, if it is at beta, dehydration happens, internally. But if it
Hmm.
is gamma, delta, then again esterification is taking place. Okay.
Okay.
If at all I have, you know, epsilon and above, if at all I have epsilon and above, then instead of making a cyclic compound, which will be again 7-membered or 8-membered ring, which is unstable, the esterification happens between two molecules on both ends. And that will continue till it becomes a polymer like this. Okay.
Hmm.
So it will keep on happening till polymer is formed.
Yeah.
So this type of polymer is called polyester because you're making an ester. So this is the sequence of preparation of polyesters. Got it? So we need to have carbons, that is methyl groups, greater than or equal to 5. Then that will happen. Okay. Next.
Wait, so, sir, this
Yes, beta.
polyester that we get, what do we get it in the form of? Is it like a
Fiber,
solid?
like a fiber. Okay.
Yeah, yeah, I know that, but obviously it's not gonna, when you do the reaction, it's not gonna come out as like a piece of cloth or some
No,
string.
no, no.
So
Cannot be
yeah,
like
that's what I'm asking. How does it form? Like, how does it like?
like a lump. Okay. So it will be like a thick lump, correct? Which you have to spread it over, correct?
Hmm.
You have to process it further. Understood? Clear?
Okay.
And try
Yeah.
to remove whatever the moisture because this will again happen with an aqueous solution, right? So you have to
Hmm.
keep on removing moisture, dry it out. Okay. So as it happens, then the appearance will be more fibrous. Okay.
Okay.
Right. The same logic how we did for alpha hydroxy acid, you have to do the same thing for alpha amino acids. Now you can see if it is alpha amino acid, you do everything same. Whatever we have conducted the reactions exactly the same. See, if it is alpha position, you can see dehydration happens between two molecules, ending up cyclic amides. Okay. Cyclic esters are called lactones. Cyclic amides are called lactams.
Hmm.
Okay. So remember the difference, lactam and lactone. Now, if it is beta position, dehydration will take place. As usual, we learned the same thing with hydroxy also. If it is gamma position, just like esterification, here also it will connect and you'll get lactams. Delta position also attack lactam. And again, if you have epsilon and above, that is x greater than or equal to 5, then you'll get polyamides. This will end up giving polyamides. Next, what is the action of heat on dicarboxylic acids? See, we have beta dicarboxylic acid here. So on heating, what would happen? Now, when it comes to dicarboxylic acid, check out if it is beta dicarboxylic acid. That means if this is alpha and beta position, we have COOH. In that case, as soon as you heat it, the oxygen from one molecule will attract H plus, breaking this OH bond, pushing into making a double bond. Because carbon has to sustain 4 bonds, it will break a bond with carbon, another carbon here,
Hmm.
pushing this bond into making a double bond here. And this is what will end up. This part will convert into carbon dioxide And this part will convert into CH2 double bond C with OH and OH, correct? And
Yeah.
this is the enol part, ene plus ol, enol.
Mm.
Enol will convert into keto part. So what are we getting? Carboxylic acid. In short, wherever you have a beta position group, you just remove
Mm.
this out and convert that into acid. Let me show you a few examples also. For instance, if at all I have COOH here, COOH here, and again I have uh, COOH here and COOH here, okay, like this.
Mm.
Suppose if at all I heat this, see, you notice this COOH, then with respect to that COH, this is its alpha position and this is the beta position. All you need to do is remove that carbon dioxide out of it. So you will get this as COOH and COOH plus 2 moles of CO2, correct?
Mm.
Now here it is alpha, beta, gamma. Now it is at gamma position.
Yeah.
If it is at gamma position, on further heating, it will undergo dehydration and you will end up getting a cyclic anhydride like this. Got it? You'll get a cyclic anhydride here on heat, correct?
Okay.
And that's what you will say. First, beta dicarboxylic acid will make a decarboxylation and that's how you get an acid.
Mm.
Next, when it comes to gamma, if you have a succinic acid, that on heating will give you succinic anhydride. Okay,
Mm.
here you can get anhydride. But if at all you have glutaric also, if you have, you can get anhydride because the ring size is 5 and 6. Okay, clear beta?
Yes, sir.
This was gamma. What about this one? This is delta position. This is epsilon and furthermore, correct?
Yeah.
If at all I have an delta dicarboxylic acid, then also you are getting glutaric acid. But when you have epsilon, see alpha, beta, gamma, delta, epsilon. These are the
Mm.
first 5.
Yeah.
So when it comes to epsilon position, now problem is if it tries to dehydrate, it will become a 7-membered ring. Instead, again the decarboxylation follows because the structure could actually wind up and come close to each other. So just like in the first case, how we did decarboxylation, same way that happens here also. Now the water will go, carbon dioxide will go. So what is left now? Ketone is left because only C double bond is left there.
Okay.
Okay. So epsilon and above that also, above that, whatever be the case is, pimelic acid, that will also convert into a ketone plus CO2 and H2. Okay.
Okay. Yeah.
So decarboxylation is clear, beta. I mean, sorry, heating effect is clear on
Yes.
acids, right? Now, decarboxylation can also be observed using soda lime decarboxylation. Okay. Now I'm studying decarboxylation as an exclusive reaction. Hmm.
Mm.
In that case, the first kind is soda lime decarboxylation. This we have learned it earlier. That is,
Yeah.
if you have an acid plus NaOH, first you'll get a salt, and the salt in the presence of CaO and heat, it will slowly start converting into R minus and CO2. And R minus will take H plus from the water which is adsorbed by carbon monoxide, calcium oxide, and that will give you alkane and OH minus. That will give you alkane and OH minus. Clear, beta?
Okay. Yeah. Got it.
Next, what is the rate of SLDC? Rate of soda lime decarboxylation. It directly depends on stability of carb anion. Okay.
Okay.
So that means you remove CO2, 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 CO2. What do we get? Minus charge on all of them.
Yeah.
NO2 is a strongly withdrawing group that will stabilize minus charge.
Yeah.
Cl is a withdrawing group. CH3 is a donating group. Destabilize minus charge. That's why rate is directly proportional to stability of carbanion and this is the rate order which you will notice. Clear?
Okay. Yeah.
This is SLDC reaction, very common. We learned in alkanes as well. Next one is beta keto acid. This also we learned in ketones. If at beta position we have a ketone, on heating, simply just above the room temperature only, decarboxylation will take place and convert it into ketones. Okay. Next one is coal-based electrolysis. This also we learned in alkanes. That is,
Yeah.
carboxylic acid has to be first converted into salt, potassium or sodium salt, then conduct electricity. Okay. So there are two reactions that happens at anode. You will notice that the carboxylate ion will convert into a radical, giving away electrons. And these radicals will slowly shred off the carbon dioxide and get R dot.
Mhm.
And R dot and R dot will terminate with each other to convert into an alkane.
Yeah.
Okay.
Yes, sir.
On the other hand, if you notice the cathode, water will act like a reducing agent, reducing group. It will take electrons, go to the cathode, and convert itself into H2 and OH minus.
Okay.
Usually, this R dot and R dot termination will happen more easier if they are not very bulky groups.
Mm.
What if they are bulky groups? For instance, if at all I take this carboxylate radical, the rate determining step suggests that you'll get a dot here plus CO2 first. And then we are expecting two dots, these two dots to terminate with each other, but this termination is not easily possible. Instead, there are two reactions that can take place. One, instead of termination this way, here I have a dot. So what would happen? This dot can take H plus H dot, convert this into a double bond. So one will become butane, the other one will become butene. But this compound is also not observed major. You know what is major? Some amount of 3-degree radical which has been formed, that amount will be reconnected with the moles of carboxylate radical and ending up giving esters. And that will become the major product. So
Okay.
remember, only in this case, if this is the case given, then your answer will be major product will be ester form. Okay.
Okay.
Next, decarboxylation also takes place as a part of ipso substitution. Okay.
Mm.
Ipso substitution as in the groups like SO3H or COOH, the acidic groups. If at all you keep them in dilute acids, then they can invite the H plus and remove out the carbon dioxide at this position where the functional group is present.
Mm.
That's why you will see the pi bond from here will attract H plus. You will get this form, and then the bond between carbon and carbon will break, making into a double bond plus CO2. Okay,
Okay.
so you'll get benzene plus CO2. Clear? Right.
Yeah.
Next is Hoffman bromamide degradation.
Mm.
See here, an amide plus 4 moles of NaOH as it reacts in the presence of Br2, it will give you amine, Na2CO3 and NaBr. Overall reaction is always, a favorite question in JEE mains. Sometimes they will ask how many NaOH groups are used. Okay, sometimes they'll ask what is the product.
Mm.
Sometimes they'll ask what happens to the bromine, like this. Okay, so questions directly related to overall reaction is also very commonly asked here. Okay, remember it like HBD, happy birthday reaction. Got it? Easier to remember that. Okay,
Yeah.
now what exactly this reaction does? In the in the short form, you can notice it is simply removing away C double bond O and connecting these two, isn't it? So it is a step down reaction. This is the first thing you should identify. Options. Okay. It is a step down reaction. That means it is trying to remove one carbon out of it.
Mm.
Clear?
Yeah.
It will generate primary amines only. Hmm?
Okay.
Second thing, primary amines only. You
Mm.
cannot get secondary amine or tertiary amine in this case. Okay, only primary amines.
Okay.
Clear, beta?
Yes, sir.
And there is an intermediate which is involved in it, and the intermediate's name is isocyanate. Intermediate's name is isocyanate. This is its structure. Clear?
Yeah.
Understood, beta?
Yes, sir.
Without even thinking much about the mechanism, can we, recall what are the things we need to learn from the exam point of view? In happy birthday reaction, first thing you should know, there are 4
Generally.
moles of NaOH. First question.
Okay. Yeah. Product.
Second, it is product is primary amine only.
Okay.
Third, it is a step
What?
down reaction. Fourth, the intermediate formed here is isocyanate. Okay,
Yeah.
got this? Yeah. These 4 points are always being asked multiple number of times as
Mm.
questions. So even without knowing any mechanism, we should be able to answer that. Okay.
Okay.
Now let's get into the mechanism. OH minus can extract H plus from here because amides are usually neutral. So they will be ready to give away H plus as well, right?
Oh,
They can be accepting H plus, they can give away H plus depending upon solvent. So solvent here is basic, so it will act like an acid and give away H plus. So you get a negative charge on this nitrogen, okay? And this negative charge is resonance stabilized. Got it? That's why it will form to some extent. A smaller composition, but yes, it would form. And once you get N minus, that will attack the bromine, removing out the other Br minus, and thus getting an N bromamide. You'll get N bromamide. Okay.
okay.
Thereafter, OH minus can attract this H plus, remove this H plus out, and you'll get N minus. Okay. And that N minus can push electrons to carbon,
Mm.
making this alkyl group to break and attack on this nitrogen, removing this Br. What is this Wolff rearrangement?
Sorry.
This is a Wolff rearrangement, right?
Huh.
Same rearrangement, if you can
Yeah.
see that. So due to this Wolff rearrangement, what is the product you are getting now? I mean, what is the compound you are getting now? Isocyanate.
Yeah.
So this is the intermediate which is formed. Earlier, when we did, unsteady reaction, we learned there is formation of ketene due to
Yeah.
Wolff rearrangement. Here it is
Mm.
forming isocyanate. Once you get an isocyanate will do very similar reactions as we did the same thing with ketones. Okay,
Mm.
you can do hydrolysis. On hydrolysis, 2 moles of water will add hydrogens to nitrogen and OH groups to carbon.
Yeah.
As it happens, two sides. See, this is the first mole, you get this one. Second mole, you'll get this one. Okay,
Yeah.
ending up what? Ending up into getting amine, which is 1 degree amine, and carbon dioxide, which is reacting with OH minus and converting into carbonate ion.
Okay.
Wherever I have marked yellow, notice that that is a position, that is a place where OH minus was utilized. And that's how you are getting 1, 2, 3, 4. These 4 moles are being used overall.
Okay. Yeah. Got it.
Clear, beta?
Yes, sir.
Very, very important reaction from this topic. Okay, it's an overlap topic. It is the same thing which can be used in amines also. So, but I suggest you go through it once carefully, then we'll go ahead. Check, take a minute, check it out, and then we can go ahead.
So done.
Finished?
Yes, sir.
Next, let's see what are the limitations of, you know, HBD reaction. One limitation is if the alkyl group is very large, that is more than 6 carbons, then the Wolff rearrangement becomes very slow process. That's why you cannot expect that Wolff rearrangement to take place easily.
Mm.
So that means HBD reaction is more valid as long as you have a smaller alkyl groups. Okay. If it is a cyclic group, still it happens.
Mm.
Cyclic structure will be easily movable, but a long chain is difficult to move. Okay.
Okay. Yeah.
What I meant to say is, don't think in terms of benzene. Like, sir, what if you have a benzene? Benzene will move better. Like,
Yeah.
suppose if you have a group like this, Br and minus is there, definitely this phenyl will move. This group will go here. Br minus will come out. Okay, this will happen. So cyclic structures will move more easily. But if it is a straight chain alkyl group, after 6 carbons, it becomes difficult.
Mm.
Now, if you have at alpha position, you already have a halo group or a OH minus group, halo or hydroxy, any group, then the product is not amine exactly, it is aldehyde. Instead of amines, you get aldehyde. Okay. See, the mechanism goes the same way. First, you will be making this form, then and Wolff rearrangement will take place, isocyanide will form. Up to this, there is no change. After isocyanide is forming, as the hydrolysis happens, right, you will get this as OH2. I mean, you will get this as OH here and NH2 here, correct? This is
Mm.
the product which you are expecting, correct?
Yeah.
But here, oxygen, it is in a acidic medium, so lone pair from oxygen can push, remove out this NH2 minus. And the NH2 minus can take H plus from water, convert itself into ammonia. So what is left here now? What is left here is aldehydes. So that's why if you have a hydroxy group or a halogen group already, instead of getting an amines, you will get aldehydes. Okay. Even if you have a C triple bond C here at the alpha position,
Mm.
at, at the alpha position, if you have a triple bond here, then same Wolff rearrangement will take place. From this carbon, it will attack nitrogen, it will go here, Br minus will come, you will get this isocyanate. And that on hydrolysis will give you amines, and amines with OH minus will give you imines. It will push once you get, uh, NH2 minus here, correct?
Mm.
Understood?
Yeah.
So this NH2 minus will push electrons here, pushing this minus charge here, and that will keep on happening till it becomes cyanide. Okay. So what is the product you will get? Nitriles. So instead of getting aldehydes or amines, you'll end up getting nitriles.
Okay.
These three are the limitations or exceptions. Usually only ask for J advanced. Okay, but otherwise in mains, these reactions are not there. Means simply you need to know if there is an amine group given. I mean, if there is an HBD reaction given, amine group is what you will search for. Done
Yeah.
better.
Yeah.
Here. Okay. Now, what are the reactions which are very, very similar to HBD reaction? Okay. There are three other reactions. Okay. Although as a name, they might not be asked in the exam, but the reaction could be given. See, the first one is Curtius reaction, wherein if I use an acid chloride, react that with azide, that is N3 minus. So N3 minus will get connected here. You will have this connection like this. And
Mm.
then R minus will go connect onto this nitrogen. Minus charge will be pushed here. N2 group will be out. So what do I get? Rn double bond C double bond O. This is isocyanate.
Mm.
Correct? You got the isocyanate. Same way, Lawson's reaction. Lawson's reaction is when you have a hydroxyl amide. I have a hydroxyl amide. When you react with TSCl, this is tosyl chloride.
Mm.
So OH will become OTS, a good leaving group. And then OH minus can extract H plus from here, gets a negative charge on nitrogen. Again, you can see Wolff rearrangement is possible. R minus can go, N minus can become double bond, OTS can leave.
Yeah.
Again, you will get isocyanate. So whether it is Curtius, whether it is Lawson's, you will get isocyanate. Last one being Schmidt reaction. Here also, lone pair from acid can take H plus and
Mm.
this becomes N3 minus. And because of it, this becomes a good leaving group. N3 minus will attack back and you'll get azide carboxylate. Hmm. Same as this is same as Curtis reaction. Here, instead of using acid, you are using acid chloride. Here, I'm directly using acids.
Okay.
On doing that, you will get an azide group here. Azide structure is like this. Now, N minus already has it. It will close double bond. R minus will attack here. N2 gas will be relieved. So, you will get this as isocyanate. Clear?
Yeah.
Any issue there?
No, sir.
Right. Next, check out reduction of amides. Any amide groups, if you have, if at all you reduce them, they'll also convert back into amines. Okay.
Mm.
Clear beta? Typically, lithium aluminum hydride is a better reducing agent to convert them into amines. Done.
Yeah.
What is the general reaction of acids to get acid chlorides? See, you react with SOCl2, PCl5, CCl3, POCl3. These were all the reactions we used in alcohols.
Mm.
Alcohols to convert into alkyl halides. So that means you remove the same OH group here, get an halogen group there. This reaction is also happening via SN2 kind. Hmm? Correct?
Yeah.
Hmm. Next, Hunsdiecker reaction. Hunsdiecker reaction is when you have a carboxylic acid reacting with a moist Ag2O. See, with moist Ag2O, first you'll get a silver salt. Okay, because Ag2O is basic in nature. Acid-base reaction will take place. Thereafter, when you react with a bromine in the presence of light, then the Ag from here will start uh, attracting bromine, convert into AgBr. Okay, and this part will get decarboxylated, and R dot and Br dot will convert into RBr. Okay, see the mechanism steps. This is a silver salt react with Br2 in the presence of light. So you will get this as AgBr forming here and RC double bond OBr will be forming here. Now, in the presence of light, this bond will again break into dot here and dot here. So that's how you'll get bromine radical and carboxylate radical. And just like in coal-based electrolysis, we learned that once you get a radical, they will be slowly decarboxylating.
Yeah.
So CO2 will go away, R dot will form, and this R dot will react with Br2 again, remove out one more Br, gets this as RBr. Done. Clear?
Yes, sir.
Right. Next. Check out COOAg here. Okay.
Mm.
When you react with Br2, first silver will become AgBr and this carbon will convert itself into CO2. So Br dot will come here. Okay. See, a radical can exist in non-planar carbon also at bridge position. If it was carbocation or carbanion, this will not happen. But since it is at radical form, this reaction can take place. Okay.
Mm.
Hmm. The next reaction being HVZ reaction, Hell-Holhard-Zelensky reaction. Okay. Name sounds very big, but yeah, reaction is simple. Okay.
It sounds like a vampire's name.
Yes. True. Okay. Notice this. If you have an alpha halogen happening on carboxylic acid, it is called HVZ reaction.
Mm.
The necessity condition or the requirement here is the alpha position carbon should have at least one alpha hydrogen. Hmm? And it should be sp3 carbon. It cannot be sp2 carbon, right? All you need to do is reuse red phosphorus and halogen, chlorine, bromine, or iodine. So the hydrogen will be replaced with halogen. That's the simple reaction which will take place. Okay.
Okay.
So how does it happen? Red phosphorus will react with chlorine, convert into PCl3. PCl3, when you react with carboxylic acid via SN2 mechanism, this OH will go, Cl will come. Okay.
Mm.
And this is the slow step. That is, the acid chloride will start showing an enol character. And
Mm.
from this enol character, the pi bond will attack on chlorine, remove this chlorine away. Chlorine gets substituted. Cl minus will take H plus and converts into alpha chloroacid chloride. Hmm? Alpha chloroacid chloride. And this, as you react, this is the first mole. Imagine this is the first mole. Okay. Sorry, first mole. And the second mole, okay, as you see the second mole will start now converting into acid chloride, giving this OH here. This is kind of an exchange that will take place. And you will start getting up this one. And this acid chloride again goes with this reaction here. So it is like this. First mole is alpha chloro acid chloride. As it interacts with the second mole, this second mole will become acid chloride and this will become acid. Okay.
Okay.
Here, just a second. Notice, if you may have noticed that the rate determining step is only about this enol formation. Okay, it's a very slow step. That's why whether you do reaction with chlorine, bromine, or iodine, the rate will be same. Rate of the
Mm.
reaction will be same. Okay, Shana clear beta?
Yes, sir.
Right. HVC reaction has a lot of advantage. That is, if you have an alpha halo acid, if you react with ammonia, ammonia will make a reaction here, remove chlorine. So you'll get alpha amino acids. If you take OH minus, OH minus can attack here, remove Cl minus, you'll get alpha hydroxy acid. See, alpha hydroxy acid is nothing but lactic acid. Alpha
Mm.
amino acid is nothing but proteins. A basic
Yeah.
form of protein is alpha amino acid. Okay. So you can see the advantages. You can get a lot of products that we require in general. Okay. Now in the reaction, if you notice, okay, this is let's say it is an R configured carbon.
Mm.
If I react that with dilute aqueous NaOH, okay, or if I take directly react with water, in both cases you will notice that the R remains as R and converting into S is less. Major product will be this one. Why is that so? It will follow SN-NGP mechanism. Okay, what does that mean? Let me show here. Suppose if you have a leaving group like this, chlorine is a leaving group here, okay?
Mm.
And then we have this carbon having a double bond here, right? Sorry, O minus here and a double bond O here like this, correct? So before the water or OH minus can come and try to replace chlorine, this oxygen itself will attack internally and remove this. So thus getting an oxide linkage like this. Understood? But obviously here it will be unstable form. And that's when water or OH minus, you can take OH minus also, that will attack back here. It will break this. And again, you will get this as CO minus, double bond O and OH. Okay. OH2 plus, or which will convert into OH, correct? So
Okay.
if this configuration had, let's say, R configuration, correct? After removing the chlorine, what will it become? S configuration, because it was an anti-attack. And
Yeah.
again, you are making an anti-attack. So finally, what do we get? R configuration. This type of internal adjustment to retain the configuration is called SNNGP. Okay, so that's what you would notice. SNNGP is happening in this case. That leads to the major product becoming R only. So if chlorine is here, at the same position, you have to put OH. Okay, HVC is clear, beta. Carboxylic acids, benzene carboxylic acid will also be involved into electrophilic aromatic substitution also. That is, at the uh, meta position, we can get a nitration happening because COH is a withdrawing group. It is meta directing group. Okay. But if at all I react that with, uh, if at all I react that with OH minus, this OH minus can take H plus from here, convert into carboxylate here. Got it?
Mm.
And CO minus is a donating group, because of which now the nitration happens at ortho position or a para position. Para usually is major.
Mm.
Okay. Same way, if at all I react with iron with Cl2, Cl plus as a electrophile can attack at ortho position or para position. You'll get these two products. Thereafter, if you do hydrolysis, you can get that H back here. CO minus will take away that H back and you'll get these products. Any doubt here, beta?
No, sir.
Clear?
Yeah.
Right.
Are we going to finish the chapter in this session?
More or less, yes.
Okay.
Check out what is the test for carboxylic acids. Okay.
Mm.
Sodium metal test. Right. Of course, we learned that it will give H2 gas. It is an acid, so it will convert blue litmus to red litmus.
Yeah.
It can give a brisk effervescence of carbon dioxide, that is sodium bicarbonate test. It can form esters, which is fruity smell with alcohols.
Mm.
Only formic acid can give a white PPT of Hg to Cl2. Okay. If we
Mm.
treat with FeCl3, FeCl3 can get attached with RCO minus and give a red coloration. With carboxylate, it will form a complex, which is a red coloration.
Mm.
Okay. And lastly, formic acid or oxalic acid, both of them. Formic or oxalic acid, they can react with KMNO4 to convert that into Mn plus 2. KMNO4, which is purple, becomes colorless. So this test is for specifically for formic acid and oxalic acid. Only for formic and oxalic acid. Okay.
Mm.
Correct. So these are typical tests of carboxylic acid beta. Understood?
Yes, sir.
Right. Okay. Just a minute. We'll take a 5 minutes break and then we'll catch up again. Okay.
Okay.
Right. When it comes to esters, right? IUPAC name of the esters. First thing you need to realize how it is to be written. Every time you have an carboxylate group here like this, the first thing you will read out is what is it present on the oxygen. That should be written first without any numbering on it. So this will become isopropyl, and then you start numbering the main chain. So this is propane with a 8 here. So that's why it is called propanoate. This is a carboxylate, right? This is a
Yeah.
carboxylate form. So that's why it is called propanoate.
Mm.
Isopropyl propanoate. That is the IUPAC name. Same way, methyl methanoate.
Mm.
If you have esters on both sides of this straight chain, then you need to mention what is the groups which are present at these two ends. These two are ethyls. So I can write it as ethyl pentane 1,5-dioate. Okay. In case if you have a ethyl and methyl, two different groups, then you can write it at the numbers also, that one side we have ethyl, one side we have methyl. and it is an hexane with 1,6-diO8. Now, the
Okay.
important part comes when you have a cyclic structure. In case of cyclic structure, what you will do? See, in cyclic structure, the numbering starts always on the cycle, not on the functional group, correct?
Mm.
So the functional group never gets rewarded with a number, correct?
Mm.
It will be present on a cycle's first position, but the functional group's carbon itself will never be rewarded with a number. Hmm?
Mm.
So in such cases where the functional group carbon does not get a number, then you will use the word carboxyl,
Mm.
right? So we do not write simply O8, we write it as carboxyl O8.
Okay.
So that becomes, now it is ethyl cyclohexane carboxylate. Okay, clear?
Yes, sir.
This is a common uh, name that is being used a lot. That is diethyl malonate because it is a derivative of malonic acid. Okay, DEM means dimethyl malonate. Got it? By
Yeah.
chance, if you have a ketone instead of an acid here, it is basically ethyl 3-oxobutanoate, IUPAC name. Common
Mm.
name that is typically used is acetoacetic ester or
Mm.
ethyl acetoacetate. Acetoacetic ester or ethyl acetoacetate. Next, check out esterification. Carboxylic acid plus alcohol. If you react both of them, you know that esters will come. This is called Fischer esterification. This we have been learning earlier only. If you use the same with diazomethane also, diazomethane can take H plus away, converts into carboxylate. Carboxylate can act like nucleophile, remove out nitrogen. You will get methyl esters. You will get methyl esters. Hmm?
Mm.
Another way of making esters is Baeyer-Villiger oxidation. Baeyer-Villiger oxidation is when you have a ketone using MCPBA, that is, peroxy acid, any peroxy acid, it will make an insertion of oxygen on either side, depending on the
Mm.
migrating aptitude. Okay. So you can see this is a migrating aptitude we have. 3 degree is greater than cyclohexyl, greater than 2 degree, then phenyl 1 degree, and methyl. Of course, hydrogen is the highest, hydrogen and then 3 degree. Okay.
Okay. Yeah.
So that way you will have ester formation. Okay. If you take anhydride, react with alcohols, again you will get one ester and one acids, just like
Mm.
esterification. Acid chloride with alcohol will also give you ester and HCl, just like esterification. These are similar reactions like esterification. Ketenes and alcohols, just like aldehydes ketones addition, here also H will get added here, OR will get added here. So that's how you'll get esters. Okay.
Mm.
Lastly, Tischenko. Tischenko is an alternative for Canizero. So instead of using NaOH, we'll be using alkoxy aluminium. So this is ethoxy aluminium here. So what you need to do when you take 2 moles of aldehyde, convert 1 mole into acid, 1 mole into alcohol. Then react both of them to get ester. That is how Tischenko works. Okay.
Okay.
And next, if you have a carboxylate, you attack on alkyl halide, remove this X and you'll get ester form. Clear? Right.
Yeah.
Next, what are the properties of esters? See, fruity smelling compound. It has to be fruity smelling compound. High volatility due to lack of hydrogen bond. Got it?
Yeah.
General reaction is this. If you have any nucleophile attacking on carbon, which is at sp2 carbon, that will convert into an sp3 carbon first. Reaction, it will push and remove OR group. Right? That's how the substitution takes place. This is normally called as SN2 also because it is overall like a SN2 reaction, but forming through an intermediate. Okay.
Yeah.
Because it is undergoing an addition first and then elimination, it is also called as SNAE reaction, substitution via addition elimination.
Mm.
Got it?
Yeah.
Hmm. Now, this is the only reaction esters will do. That is SNAE that will do. That means it will get addition, then it will get elimination done.
Mm.
But while you're doing this reaction, how does it happen in acidic medium and how does it take place in basic medium is what our discussion is.
Mm.
Check out in acidic medium. If you have an ester, you react that in acidic medium like H plus.
Mm.
What is the mechanism that can take place? See, the lone pair on oxygen can take H plus, converts into OH plus. Water can attack on this carbon. Pi bond could shift onto this oxygen. You will get this product.
Mm.
And from here, the lone pair on this oxygen can take H plus, convert into ROH plus. And ROH plus is a good leaving group.
Mm.
So lone pair can push here. This alcohol can be coming out. That's how you'll get an acid and an alcohol. So you'll get acid and an alcohol here. Clear?
Okay.
Okay. So what do we get here is, you know, it is an acidic medium, bimolecular reaction, and an acyl cleavage is observed.
Mm.
You can see an acyl cleavage is happening, correct?
Mm.
And the rate of the reaction will be equal to substrate concentration into water. You can see this is the RDS, this one into this one, correct? So there are two molecules involved in this mechanism at the rate determining step. Yeah. In the rate determining step, two molecules are involved. So that is called molecularity 2. Hmm? So this type of mechanism are given as an abbreviation. What is that? A means acid catalyzed. AC means acyl cleavage. You are cleaving at an acyl bond. CO bond you are breaking here eventually. That's why it is called acyl cleavage. And while doing it in the mechanism, you will see there are two molecules involved in the rate determining step. So that's why it is called 2. Just like how we write SN2,
Mm.
SN1, like that, this mechanism is called AAC2.
Okay.
Any doubt?
No.
Second case is the braking could also happen between, why need to be done here? It can happen between oxygen and R also. That way also we can make an reaction. So if that happens, if that kind of braking happens, then it is called alkyl cleavage. Earlier it was acyl cleavage, now it will be alkyl cleavage. Okay.
Okay.
So you see, first protonation will take place, and then you got OH here, and immediately the bond will break onto this side.
Mm.
So as it breaks here, you know, as it breaks here, so we will get this into an acid form, and R dash plus will form. What is R dash plus? R dash plus is a carbocation that on hydrolysis will convert into alcohol and acid. So again, we are getting the same product, but now the breaking of the bond is different. Hmm?
Yeah.
So now how do we read the mechanism? See, this is acid catalyzed, alkyl cleavage,
Mm.
and in the rate determining step, this is the RDS reaction. Okay, this is the rate determining step. So in the rate determining step, you will see only one molecule is involved. That's why it is called AL1. AAL1. Is that clear with these 2 points?
Awesome.
Next is base catalyzed mechanism. In esters, if you add NaOH, then OH minus will go attack on carbon. First, it will become SNTD. So O will push here, RO minus will go out. This is the rate determining step again. Okay, clear?
Mm.
Oh, sorry, not this one. Here, I have written it. Clear? Rate determining step here. So in this case, RO minus is leaving, acid is forming, RO minus will take H plus and you will get carboxylate and alcohol. Now you notice this mechanism here. It is a base catalyzed mechanism. It is also making an acyl cleavage. And how many molecules are involved in this? two molecules are involved. So it is BAC twice. Okay, clear, beta?
Yeah.
Now, typically this reaction is observed, when you are trying to make, when we are making soap in industries. Okay, so these are called triglycerides. These are triglycerides.
Mm.
Triglycerides are, fatty acid contents that when you react with OH minus will attack here, make an acyl cleavage, and acyl cleavage. On doing that, what do I get? You will get, 3 moles of this acid form. This is called stearate. If it is with sodium, it is called sodium stearate. Sodium stearate is the soap. Okay. And along with that, what is left over? Glycerol. So it is both preparation of soap as well as preparation of glycerol. Now, this reaction is not going to be backwards because this is already very stable as in carboxylate form. If it was having OH, then esterification could happen. The reaction would go backwards. Okay. So here, no reaction will go backward here. So this is a saponification reaction. Clear, beta?
Okay.
Right. So you can see R and R dash, both of them are simple groups like methyl, ethyl, phenyl, and so on. Okay. If they are simple groups, the mechanism type will be AAC twice. If R dash is bulkier and it is a stable carbocation which you are able to generate like this is a 3-degree carbon, then the bond breaking will happen on this side. Mechanism will be AAL1. It will be AAL1. So therefore, you have to break it here. You will get this acid plus alcohol. Okay. The other type will be AAC1 also. AAC1 means acyl breakage, but only with one molecule. I mean, rate determining step, only one molecule is involved. See, first on hydrolysis, you'll get this part. And then bond is breaking on the acyl form to get a carbocation here so that the lone pair can uh, help it to get a stabilization. And thereafter, water can attack, you'll get an acid here. So, in the process of breaking this bond, we are not utilizing any nucleophile to attack, right? It is breaking on its own. Usually, when that happens, when this side there is a lot of bulky group, on the carboxylic side there is bulky group, so that will not allow nucleophile to attack easily. But naturally, it will break on its own because here the oxygen can stabilize that positive charge. Okay. And that's the reason why you will get an acid here. Okay.
Okay.
And notice one thing here. If both R and R dash, that means this side as well as this side, these two are bulkier, then no reaction will take place. Done. Now, while adding with a basic medium, we have learned that this is going to be, BAC twice. And in the rate determining step, if you have a withdrawing group here, OH minus will attack faster. So the rate will be dependent on these groups. If the groups are withdrawing, the reaction is faster. You can check it out.
Yeah.
Clear it up?
Yes, sir.
Next is ammonolysis. Okay. So if you have an ester react with ammonia, ammonia will attack here. RO group will come here. So you'll get an amide and alcohol. This is ammonolysis. Got it? So esters, when you react with excess of amines, you'll get these amine forms. On further heating, this part, that is MENH hydrogen, all of them will go away as methylamine and you'll get a cyclic structure, which is N-methyl phthalimide. Internal attack can also take place. Nitrogen can attack internally, remove OMe, and you'll get this product, which is lactam. Okay.
Yes, sir.
Transesterification also we learned in alcohols, wherein one ester is generating another ester, considering the alcohol is being given at a larger composition. Okay.
Okay.
If you have an ester, you react with PCl3 SOCl2 or PCl3 here, PCl5 SOCl2 or PCl3 here.
Hmm.
In that case, this will become acid chloride here. Okay. Methanol, SO2 and H3PO4. All of this would be formed here. Got it?
Okay.
Next. If you make reduction reaction here, got it? So you will see uh, esters can undergo reduction, not with hydrogen, but lithium aluminum hydride, lithium boron hydride, dival H, but will end up at aldehyde, and with sodium and ethanol. These are the reducing agents which you will notice. We have done this reducing part before,
Yeah.
but again, I'll teach you one more time about all the reducing agents and oxidizing agents at one place. Okay. Hmm.
Okay.
See this reaction. We have an carboxylic acid. We have an ester on both sides. See with B2H6, we know that it is excellent reducing agent only for acids. So acid will get reduced. Nothing will happen to ester.
Hmm.
Now internally we have an acid and an ester. So it can attack, give a cyclic ester form here. Okay. If at all I use lithium aluminum hydride, this will also get reduced. So you'll get alcohol. Okay. Next one is, this is the last part of it, which is Claisen condensation. Hmm. Claisen condensation, if you notice that, it is like an aldol, but for esters. Same aldol form, but for esters. Okay. So you take these 2 moles of esters, react with a base, and typically take the base which is very similar to this alkoxide. Hmm. So if I take ethoxide as a base will extract H plus from the alpha position. You get a negative charge. So enolate ion is formed. Enolate ion as a nucleophile attacks the second mole. You will get SNTD addition. And then as oxygen will push it as a double bond, OET will go away, and that's how we'll get beta keto ester. Okay, this is how we get beta keto ester. Clear, beta?
Yes, sir.
So if alpha hydrogen is present with some alkyl groups, which is bulkier,
Hmm.
in that case, ETO minus is not strong base enough to remove this hydrogen, because you will be ending up getting a 3-degree carbanion, right? So that's why getting a 3-degree carbanion with this base is not possible. That's why you need to use much stronger bases. That includes this one, triphenyl carbon, H minus, R minus, NH2 minus, or even NH2 minus. These are some strong bases. When we take those strong bases, then you can generate this carbanion, and this carbanion can attack the second mole. Got it? Just a second. Hello. Sorry. Okay. So you can see the C minus would attack on this carbon, and that's how it will end up getting a beta keto ester form.
Okay.
Clear, beta?
Yes, sir.
Next one is cross collision. Same, just like cross aldol. Now we have cross collision. So one is when you react with E2 minus, this can make a self cleavage. That means you can get a self beta keto ester. This can make a self beta keto ester. These two are self forms. Hmm. The cross form is this one. That is when CH2 minus attacks here and remove OAT, you will get this one. Or if this CH minus will go attack here and then you remove this OET, then you'll get this one. So how many? Two cross and two self. Just like in aldol also we get two cross and two self. Here also we'll get two cross and two self. Notice that there is no chiral center here, but there is one chiral center here and here. So that's how it makes total product as 6.
Okay.
Okay,
Yeah.
right. Same way, here also you can see at this position, sixth position onwards, I can make an intramolecular cleavage now. So from here it can attack, OET can be removed, and you'll end up getting beta keto ester. Okay,
Yeah.
these are all intramolecular cleavage reactions. Okay, usually when it comes to beta keto ester will not be giving this FeCl3 test as much as beta diketones. That is, suppose if you have a ketone here, this ketone will have more enol content than keto content.
Mm.
Okay, and Fe plus 3 will only respond to the enols which are in larger quantity. So this is around 90%. So Fe plus 3 will respond and convert into a violet coloration. Okay, but
Okay.
since beta keto ester, its major content is keto form and hardly any enol form. That's why it does not respond to Fe plus 3 test.
Mm.
Clear beta?
Okay.
So when the product is forming, you just need to check whether it is giving a coloration or not. If it is not giving, that means it must be beta keto ester. Okay, got it? This is the same reactions which we did it in aldehydes and ketones. I've just given it again. Okay,
Yeah.
and the last reaction is about acyloin condensation. So acyloin condensation is exactly same as we did earlier for uh, benzene form. We have done this same with benzene form earlier. Let me explain you how.
Mm.
If you have an ester in the presence of sodium and xylene, electrons will be supplied to the carbon here. So 2 moles will get C dot groups. C dot and C dot will terminate to get this form. And then O minus will push, RO minus will come out. O minus will push and RO minus will come out. And that's how you end up getting a keto form. Okay.
Okay.
And thereafter, again, sodium can help getting 2 electrons here, 2 dots, and that will end up getting a double bond. And now on hydrolysis, you'll get an enol form. Can you see it is an enol? So that enol will tautomerize and convert into keto form. So what are
Mm.
we ending up? Alpha hydroxy ketone, and alpha hydroxy ketone is called acyloin. Okay,
Yeah.
that was an acyloin between two molecules. That can happen within the molecule also. So that is intramolecular acyloin. What you need to do, you just need to remove OET and OET, join both these carbons. So you'll get a 6-membered ring and make one carbon into OH group. That's it. That is the overall reaction.
Okay.
Chana clear beta?
Yes, sir.
That's it. This is what you have it for carboxylic acid. Okay.
Yeah.